Good morning, students. This is M. Prasant Raju. Stand before you to complete the last unit 5 of Applied Physics Part 2, namely Dielectrics. In this Dielectrics of an atomic view, I would like to explain a few of the definitions. The first one is known as Dielectric Polarization. Let us see this dielectric polarization. What is dielectric polarization? When a dielectric material is placed inside an electric field, such dipoles are created in all the atoms inside. That means the process of producing electric dipoles which are oriented along the field direction is called polarization in dielectrics. We usually divide the dielectrics of the molecules into two types. One is called dielectrics of polar molecules and dielectrics of non-polar molecules. Now, based on dielectrics of atomic view, we would like to explain the second definition, which is called dielectric polarizability. What is dielectric polarizability? Let me explain the definition of dielectric polarizability. When the strength of the electric field E is increased, what happens, the strength of induced dipole mu is also increases. In this dielectric polarizability, strength of electric field is denoted by E and induced dipole is denoted by mu. So, we have two relationships between E and mu. What is that? The induced dipole moment is proportional to the intensity of electric field. If you take this equation, that is mu directly proportional to E, if I would like to remove this proportionality, I would like to put one proportionality constant. This is called proportionality constant. What is that? Mu inversely directly proportional to E, therefore mu is equal mu into alpha I into E. This alpha I is called constant of proportionality, which is termed as dielectric polarizability. Now it can also be defined as induced dipole moment for unit electric field. So the two most definitions, which is called dielectric polarization and dielectric polarizability. Dielectric polarizability is explaining about the nature of the substances. Suppose if you take strength of electric field E of any substance, if it increases, strength of the induced dipole mu is also increases. So here mu and E one and another are directly proportional quantities interlinked with each other. Now we would like to go for the third definition, which is called dielectric constant, and it will be denoted by epsilon suffix r. How do we define this dielectric constant? It is the ratio between permittivity of the medium and the permittivity of free space. If you look at this equation, in this equation, epsilon r is equal to epsilon by epsilon naught. My epsilon r is called dielectric constant, and the another name for this epsilon r is called relative permittivity, and epsilon is called permittivity in medium, epsilon naught is called permittivity of free space. Suppose if you take this epsilon naught, whose value is constant, which is around 8.85 into 10 power minus 12 coulomb square per Newton meter square. That is the standard value of permittivity of free space, and let it be denoted by epsilon naught. After completing this, my dear students, we would like to take this the third definition, the fourth definition, which is called electric susceptibility. Electric susceptibility is defined like this. Basically, electric susceptibility is denoted by Xi. When a dielectric material is placed in an electric field, then the dielectric is said to be polarized. So, when do we say that a dielectric substance is going to be polarized? There is certain rules which is known as, whenever if you bring dielectric materials, bring it and put it in electric field, first of all what you get said is, the dielectric is going to be polarized. That means there are two vectors. The first vector is polarization vector, let it be denoted by P, and it is proportional to the applied electric field E. So strictly speaking, P is a vector quantity, its name is polarization, and E is also a vector quantity, it is named as electric field intensity. So if you look at the mathematical relation, which is called P directly proportional to E, if you remove the directly proportional relation, we would put a constant. That constant is called P is equal to Xi, and where Xi is called proportionality constant, and it is called the susceptibility of the dielectric material. So if you want to define electric susceptibility Xi, and it is a ratio between P versus E. So how do we define the dielectric material here? The dielectric material is represented by, strictly speaking, Dielectric material is electric susceptibility is denoted by psi is equal to P by E. So in the numerator position, polarization vector, and in the denominator position, it will be having a E. What is that E is known as intensity of electric field. Therefore, the susceptibility of dielectric material is defined as ratio of P to the E. Then coming to the most important essay question expecting from this unit, that is dielectrics part, relation between three electric vectors D, E and P. My D is called electric displacement, and my E is called electric intensity of the field, and P is called electric polarization. So when a dielectric material is placed between the plates of a charged capacitor, then the charges are induced on the surface of the dielectric. So to take the expression from DEP, we could take like this. Let Q dash be the induced charge on the dielectric, and the electric field E dash is due to these charges, which is in the opposite direction to the electric field E naught due to the charges on the capacitor plates. So therefore, strictly speaking, the resultant electric field between the plates is E is equal to E naught minus E dash. How do we write this? In this equation, E naught is equal to Q by epsilon naught A, and E dash is equal to Q dash by epsilon naught A. Suppose if you take parallel plate capacitor, I can represent that E naught is equal to Q by epsilon naught A. So that means my intensity of electric field at free space is directly proportional to charge and inversely proportional to permittivity in free space with area of cross section. So we could write E naught is equal to Q by epsilon naught A and E dash is equal to Q dash by epsilon naught A. And substitute these two values in the above equation, we will get E is equal to Q by epsilon naught A minus Q dash by epsilon naught A. Take Q by epsilon naught as common here. E is equal to 1 by epsilon naught into Q by A minus Q dash by A. And taking cross multiplication from this step, I will get epsilon naught E is equal to Q by A minus Q dash by A. And this Q by A is take from the right hand side to left hand side. I will get Q by A is equal to epsilon naught E plus Q dash by A. And as I know that the electric displacement is nothing but the ratio of induced charge to the area of cross section, I can represent it with it as Q by A. Therefore, in place of Q by A, I can put D, that is equal to epsilon naught E plus P. So strictly speaking, that my D is called electric displacement, and P is called electric polarization, and E is called intensity of electric intensity. Therefore, strictly speaking, as I told you that the heading of this topic is relation between three electric vectors D, E and P, which is nothing but called my relation is D is equal to epsilon naught E plus P. My D is called, once again I am repeating, my D is called electric displacement, my E is called intensity of electric field, my P is called electric polarization. So that is why I am writing here where Q by A is equal to D and Q dash by A is equal to P. This is what is known as the relation between the three electric vectors D, E and P, where D is called electric displacement, E is called intensity of electric field, and P is called electric polarization. Now we would like to enter into the another topic, which is called types of polarization. How do we say that the types of polarization is going to be split up into the three types? Based on the characteristics of dielectric views of an atomic view, I would like to classify the types of polarization into three types. Number one is called electronic polarization. Let me tell you what exactly electronic polarization is telling. An electric strain produced in an atom due to the application of electric field is called electronic polarization. That means the extent of displacement of charges is proportional to the strength of the electric field. So there are two parameters which are very much directly proportional to one another. The number one is called mu E. Mu E means intensity of electric field with respect to induced dipole moment. My mu E is called induced dipole moment, and my E is called intensity of electric field. So that is what is known as, strictly speaking here, we could say like this. So therefore, the intensity of electric field is with respect to the mu E. What is mu E here? My mu E is called induced dipole moment. which is always directly proportional to the intensity of electric field. Suppose if we remove this proportionality, what we have to do here? This proportionality has to be removed. Immediately we have to put one constant, and that constant we are named it as proportionality constant, and mu E is equal to alpha E into E. What is this suffix E represents here? Electronic polarizability. So my electronic polarizability is nothing but alpha suffix E. When mu E is equal to alpha E into capital E, I can call it as equation 1, and in this equation 1, my mu E is called electronic polarizability and my E is called intensity of electric field. Therefore, dielectric materials are mainly shown in this kind of polarization. If you take any dielectric material, all dielectric materials are shown by this particular kind of polarization, that is nothing but electronic polarization. And the next point is electronic polarization is extremely rapid. The electronic polarizability increases with increasing volume of atoms in the dielectric material and is independent of the temperature. So let me explain this point here. The electronic polarizability increases and with increasing of volume of any atoms in the dielectric material because it is always independent of the temperature. And similarly go for another topic which is called monoatomic gases exhibit only this type of polarization. The expression for electronic polarizability is represented by, as it is the quantitative analysis, alpha suffix E is equal to 4 pi epsilon naught into R cube. What is my R cube here? My R is called radius of the atom. This is what is known as electronic polarizability. The second topic is ionic polarization. In the second topic, ionic polarization, the ionic polarization is due to the displacement of cations and anions. We all know that anions and cations are the mobile charge carriers. When an electric field is applied to a dielectric material, the role of cations and anions is with respect to the displacement of the ionic polarization. Therefore, the ionic polarization majorly occurs in ionic solid substances. And we have one more relation about the induced dipole moment is, when the induced dipole moment is proportional to the applied field and it is expressed as mu I is directly proportional to E, mu I is equal to alpha I into E. So let me tell you what is this expression is telling here. In this equation, mu I is called induced dipole moment and E is called specifically intensity of electric field. So mu I is directly proportional to intensity of electric field. If I remove this proportionality, I will get mu I is equal to alpha I into E, and this alpha I is named as proportionality constant. We are going to call it as ionic polarizability. Now, strictly speaking here, the dipole moment for unit magnetic field at the ions is called ionic polarizability. So that means we can say the induced dipole moment for unit electric field at the ions is called ionic polarizability, and my ionic polarizability is always corresponding to the polarization. Such polarization I am going to call it as ionic polarization. For most of the materials, the ionic polarizability is less than the electronic polarizability. When you are going to take the comparative study of electronic polarizability with ionic polarizability, which one is greater between both of them? If we see, for most of the dielectric materials, the ionic polarizability is less than the electronic polarizability depending upon the characteristics of ionic polarizability of dielectric materials. The ionic polarization is independent of temperature, and the frequency with which ions that can be displaced is always up to 10 power 13 hertz. If you are going to measure the frequency of ions that are displaced with respect to its range is around up to 10 power 13 hertz. If the frequency of applied field is 10 power 15 hertz, the ions do not respond. That is why we are going to give one range of this particular ions, that is known as the frequency with which ions that can be displaced is up to 10 power 13 hertz. And similarly, if it is more than 10 power 15 hertz, they may not respond. That is what is known as the ionic polarizability. Now, I would like to explain about the expression for ionic polarizability. When an electric field E is applied to an ionic crystal, the positive ions are displaced through a distance x1 in the direction of applied electric field, and negative ions are displaced through a distance x2 in opposite direction of electric field. In this expression, I would like to take the two parameters. One is called x1 and other one is called x2. Let me explain first of all what is this x1 and what is this x2. My x1 is called distance of the direction of applied electric field with respect to positive ions, and my x2 is called the distance of the direction of applied electric field with respect to negative ions. Therefore, if you are going to take the distance between positive and negative ions, I could write it as x is equal to x1 plus x2. I can call it as equation 2. If you take a diagram that sodium and chlorine, they both are two atoms, and you are going to take the interrelated atomic radius between Na, the center point of sodium, and the center point of chlorine, which is going to be denoted by r suffix 0, and another one is known as my x1 is located at sodium and my x2 is located at chlorine. If you see the diagram A and diagram B, ionic polarization with respect to a molecule without electric field and with electric field. So, if you see the diagram A, ionic molecule without electric field, and if you see the diagram of B, ionic molecule, but it is with respect to the electric field, applying of electric field. So, there will be a Lorentz force created. The Lorentz force acting on the positive ions is say around EE. What is EE here? You know, my EE is nothing but called small e is called charge of the charge carrier, and capital E is called intensity of electric field. This is nothing but called a force. And the Lorentz force acting on the negative ions is minus EE. That means this is positive EE, this is negative EE. What is the difference between both of them? The Lorentz force created with respect to positive ions is F suffix E, that I can represent it as EE, and the Lorentz force acting on the negative ions is said to be minus EE. They both are forces. But in both the expressions, what exactly E is telling here, you know, it is the charge of the ion. Similarly, the restoring force acting on the positive ions is K1x1, and the restoring force with respect to negative ions is represented by K2x2. And I am going to represent that my K1 is equal to capital M omega naught square, and my K2 dash is equal to small m omega naught square. The both are going to be considered as restoring force constants, and where omega naught is called the angular velocity of the ions. So, strictly speaking, my capital M is called mass of positive and my small m is called mass of negative ions respectively. Therefore, when you are going to take the equilibrium condition or equilibrium position, the Lorentz force and restoring force will be equal and opposite. So, bring both of them and equating it, I can get here EE is equal to K1 x1. From this, I am taking the value of x1, which is known as my x1 is equal to EE by K1, and I can write this as x1 is equal to EE by, as I already considered that K1 is equal to capital M omega naught square, bring it and substitute in this equation of place K1, I can get x1 is equal to E by capital M omega naught square. I can call it as equation 3. Now, similarly, wrote by the third equation, E is equal to K2 x2. From this, x2 is equal to E by K2, and x2 is equal to E by small m omega naught square. This I can call it as equation 4. The time you are going to get equation 3 and equation 4, bring both of them and substitute in equation 2, we will get like this. What is that? X is equal to E by capital M omega naught square plus E by small m omega naught square, and in both the fractions I am going to take one term as common here, that is x is equal to E by omega naught square, and I will get 1 by capital M plus 1 by small m. I can call it as equation 5. The induced dipole moment is mu I is equal to Ex, and as I already told you to already get the value of x in equation 5, bring it and substitute in place of x, I can get mu I is equal to E into E by omega naught square into 1 by capital M plus 1 by small m. Again, I am going to multiply with small e versus small e with the inside part of E. I can get the final expression which is known as mu I is equal to E square E by omega naught square into 1 by capital M plus 1 by small m. I can call it as equation 6, where mu I is equal to alpha I E to E. As we already studied that this mu I is equal to alpha I E is called alpha is called ionic polarizability. My mu I is equal to alpha into E, I can call it as equation 7. Okay. So therefore, this alpha I is called ionic polarizability in this equation. So strictly speaking, that this is called alpha I is represented it as ionic polarizability. Now after finishing the electronic polarizability and ionic polarizability, the third part of polarization is called orientational polarization. It is a characteristic of polar dielectrics. In one word, we can say the orientational polarization is one of the best characteristic of the polar dielectric materials. In polar dielectrics, there are permanent dipole moments because positive and negative charges do not coincide in the molecules of the dielectric. For example, when polar dielectrics are subjected to electric field, the molecular dipoles tend to get oriented on the direction of applied field. So how do we represent this in mathematical form? The dipole moment of orientation of a dipole is directly proportional to electric field. That means mu O directly proportional to E. What is mu here? Dipole moment for orientation. And E is called what? Intensity of electric field. Therefore, mu O is equal to alpha O into E, where my alpha O is called proportionality constant, and we have given a specific name for that, which is called orientational polarizability. Now look at this diagram. First diagram A, orientational polarization due to number one is molecular dipoles when intensity of electric field is 0. That means the first one is at random condition. And if you see the figure B is representing that all molecules are in alignment. Did you understand? So orientational polarization is majorly representing about the direction of the molecules standing in which direction. Orientational polarization is due to E is equal to 0, that is figure A. And orientational polarization due to when applying of electric field, then the molecular dipoles will be represented by like this. This is what is known as orientational polarization due to molecular dipoles in the applied field. When field is there, when in presence of applied field, it will be like this, and in absence of electric field, it will be like this. Now, the expression for orientational polarizability is, we have to remember just this equation, no need of deriving this. Alpha naught, alpha O is equal to mu square by 3 kBT. Let me explain what are the terms existing in this formula. My mu is called intensity of the ionic polarizability, and Kb is called Boltzmann's constant, and T is called absolute temperature. Now after finishing this, my dear students, we are going to enter into the most important topic, which is called as Clausius-Mossotti equation. One of the most important equation expecting every time to the examination, that is what is known as Clausius-Mossotti equation. It gives basically the relation between dielectric constant and polarizability. So there is a strong relationship between dielectric constant and polarizability of atoms in a dielectric material. It says of about the Clausius and Mossotti are the two scientists who are going to perform the relationship between dielectric constant and polarizability. The dipole moment of a single atom is proportional to the internal field dipole moment, that I can represent with alpha into EI. So what is alpha here? Polarizability of the atom. What is EI here? Internal electric field. Suppose if there are Kaplan atoms per unit volume, the dipole moment per unit volume, which is called polarization. So I simply multiply this alpha EI with Kaplan, I can get equation 1, which is known as P is equal to Kaplan into alpha into EI. What is P? Polarization. What is N? Number of atoms per unit volume. What is alpha? Alpha is called dipole moment. And what is EI? Intensity of internal field. And we know that the resultant electric field at center is EI is equal to E plus P by 3 epsilon naught. We have remembered this equation. My internal intensity of electric field represents always EI is equal to E plus P by 3 epsilon naught, where EI is equal to internal electric field. And bring this value of 2 and substitute in equation 1, we will get P is equal to capital N alpha into E plus P by 3 epsilon naught. Now I am going to multiply N alpha with the internal part. I will get P is equal to N alpha by 3 epsilon naught into 3 epsilon naught E plus P. Now, bring n alpha by 3 epsilon naught to left hand side. I will get n alpha by 3 epsilon naught is equal to capital P by 3 epsilon naught E plus P. I can call it as equation 3. And we know that the relationship between intensity of electric field and dielectric polarization P, I can write it as P is equal to epsilon naught into epsilon naught minus 1 into E. So, bring this equation and substitute in equation 3, I will get n alpha by 3 epsilon naught is equal to epsilon naught into epsilon naught minus 1 into E by 3 epsilon naught E plus epsilon naught into epsilon naught minus 1 into capital E. And after simplifying this, we will get n alpha by 3 epsilon naught is equal to epsilon naught into epsilon naught minus 1 into capital E by epsilon naught into epsilon naught plus 2 into capital E. Again, in the numerator and denominator, I am going to cancel epsilon naught and epsilon naught. I will get n alpha by 3 epsilon naught is equal to epsilon naught minus 1 by epsilon naught plus 2. I am going to cancel this E also. I will get what? Therefore, the remaining term in this expression is n alpha by 3 epsilon naught is equal to epsilon naught minus 1 by epsilon naught plus 2, which is known as the important expression for, which is known as, this is what is known as the Clausius-Mosotty equation. One of the most important equation expecting from dielectric materials. It relates the macroscopic dielectric constant with the microscopic polarization. So, as I told you in the beginning of the Clausius-Mosotty equation, the strong relationship between dielectric constant and the polarization. So, my dielectric constant is related to macroscopic, and whereas my polarization is related to my microscopic property. Now, coming to the applications of dielectric materials. The dielectric materials are mainly used as insulating materials, and they will be acting as medium of capacitors. For example, first one is known as, they were classified into insulating materials. I would like to explain a few of the points coming under these insulating materials. Insulating materials shall have low dielectric constant, low dielectric loss, high resistance, and high dielectric strength. So, there are exclusively 4 parameters followed by insulating materials. All insulating materials should have low dielectric constant, low dielectric loss, high resistance, and high dielectric strength. Second property is, they are widely used in insulators and PVC materials. What is PVC? PVC means polyvinyl chloride. So, these dielectric materials are majorly extensively used in insulators and act as PVC materials, ceramic industries, mica and asbestos materials such as. And the polyvinyl chloride materials having good electrical and mechanical properties. This is one of the benefit. Why we are going to use the PVC materials are as the best insulating materials in dielectrics, you know, they have a very good electrical property and they have a very good mechanical property. And these are very much used in insulation in wires and cables. So, therefore, this is what is known as one of the best useful materials, which is called insulating materials. Now, the second one is the dielectric materials are used as capacitors. Let us see this. The charge separation in a parallel plate capacitor causes an internal electric field. A dielectric reduces the field and increases the capacitance. Every dielectric material reduces according to the intensity of electric field as it increases by the capacitance. Not only that, the dielectric materials used as best capacitors. We have a number of capacitors nowadays which are using in industries. We have cylinder capacitors and we have rotating capacitors, we have spherical capacitors, etc. like that. Number of different materials like capacitors are acting as the best capacitors, which are like dielectric materials. And the third use of these insulating materials is dielectric heating. The insulating materials can be efficiently heated up to by subjecting them to a high voltage of suitable frequency. This is one of the most important points. So, for example, if you are going to take a very important materials, now I would like to heat that material, I can use this like this. That is, the insulating materials can be efficiently heated up to by subjecting them to a high voltage of suitable frequency. If you take the microwave ovens, cooking in microwave ovens is also one of the most popular useful item for the dielectric heating. Therefore, I can take like that that the microwave ovens is one of the instrument by using this dielectric heating. And the third one is the dielectric loss manifests in the form of heat. Because when the material like dielectric is heated, with respect to the temperature, the material is not going to be damaged and the dielectric loss is very much less, and it manifests in the form of heat. That is one of the use by using this dielectric material. So therefore, once again I am repeating here, the first application of dielectric material is they are using as insulating materials. The second one is they are using as capacitors, and the third one is they are using as dielectric heating. Now I would like to enter into the most important essay question expecting from dielectrics, which is called the expression for Lorentz internal field relating to dielectric material. The electric field which an atom sees, or the electric field at an atom site, which is called the internal field. The internal field may also be defined as local field, and that is why I am going to represent with it E suffix I. What is E suffix I? E means electric field and I means internal field. It is required to know the properties of dielectric materials. And let us derive the expression for this Lorentz internal field. Consider a dielectric material and it is subjected to an external field of intensity E0. What is my E0 here? My E0 is called the initial intensity of electric field in free space. If a dipole in the material experiences this field as well as the field due to all the dipoles in the spacemans. If you look at this diagram, in this diagram you are going to see the parameters like this is what is known as E0, this is E1 and this is E3, and this is rho p, this is rho p, positive direction of rho p, this is negative direction of rho p, and my dipole cavity is existing with respect to the positive side of the spherical cavity, and my molecules were existing at central portion of this spherical cavity. Okay, cavity means pole. Evaluation of local field. How to evaluate the local field? If you look at this diagram, there is a spherical cavity existing in horizontal line, and in either sides of this diagram we have two capacitors. One is completely positive charge located, another one is negative charge located. So evaluation of local field were majorly be classified into the three types. Number one is E0, E1, E2 and E3. Imagine a spherical cavity of radius small r with the center of the reference dipole cut out from the atom. The electric field at the center of the spherical cavity is denoted by what? C. So I can write this as the internal field or local field, let it be denoted by E suffix I, which is equal to E0 plus E1 plus E2 plus E3. Let me explain the terms of E0. First of all, I would like to explain the significance of E0 in this equation. My E0 is the electric field due to the charges on the surface of the capacitor plates without dielectric. We know that the three electric vectors, let it be denoted by D is equal to epsilon naught E0. We know that D is called electric displacement, epsilon naught is called permittivity in free space, E is called intensity of electric field, and P is called electric polarization. Therefore, from this equation I can get D is equal to epsilon naught E0, and I will take the value of E0 from this expression. E0 is equal to D by epsilon naught, that is equal to, as we know that D is nothing but what? Epsilon naught T plus P. I can substitute in place of D as epsilon naught T plus P divided by epsilon naught. It is not, it is as usual. Now, if you are going to take this expression here, epsilon naught into E plus P by epsilon naught is in the form of A plus B by 2. I am going to split like this, A by 2 plus B by 2. Similarly, epsilon naught E by epsilon naught 2 plus P by epsilon naught, and then this epsilon naught and this epsilon naught cancel. We will get E0 is equal to, remaining term is E plus P by epsilon naught. Okay. Now, that is what is known as the significance of E0. Now, in the second point, significance of E1. My E1 is the electric field at the atom due to the polarized charges on the surface of the dielectric. Therefore, this field opposes the original field, and that is called depolarizing field. That means the displacement of a polarizing vector is against to the intensity of electric field. Therefore, I can represent E1 is equal to minus D by epsilon naught, or that is equal to minus P by epsilon naught. I can write like this or like this. the ratio of negative displacement by permittivity of free space, or the ratio of negative polarization to the permittivity of free space. We can represent like that also. This is what is known as the significance of intensity of electric field E1. And let me tell you the significance of E2. E2 is the electric field at center C. This is due to all the dipoles inside of the spherical cavity. So my E2 is with respect to all dipoles existing inside of the spherical cavity. And for a cubic structure, the electric field E2 is equal to 0 because it will have in symmetric structure. Therefore, the second significance of E2 is known as E2 is the electric field at center C. This is due to all dipoles inside of the spherical cavity. Now, in the expression that E0 over E1 over E2 over, now we are going to enter into E3, which is known as my E2 is the electric field at center C due to all dipoles inside the spherical cavity. Because when you are not going to apply the intensity of electric field, we will get E2 is equal to 0 because it will be existing in symmetric structure. So the significance of E2 is over. And the third one is known as E3. E3 is the field at center C due to polarized charges on the surface of spherical cavity. This is what is known as the significance of E3. Therefore, the combination of E0 plus E1 plus E2 plus E3, all these four we are going to call it as the total combination of intensity of electric field with respect to a spherical cavity, and that EI we are calling it as the internal field. What is that? Internal field or local field. We are all call this as internal field or local field. This is what is known as the intensity of electric field. Now, with respect to this, we have completed the Applied Physics Unit 5 Part 2, which is called Dielectrics. Thank you very much.